We are going to discuss about the kinetic theory of gases assumptions. We assume that all the gas molecules, they are identical, rigid, and they are elastic spherical bodies. We assume that the molecules, they are in random motion, they can move in all the possible directions, and hence the density of the gas, it remains uniform throughout the volume. Point number 3 is the volume of all the molecules is negligible. We assume that the volume of the molecule is negligible as compared to the volume of the gas. And we assume that there are no interactive forces between the gas molecules. Collision between gas molecules and with the walls of container, it is considered perfectly elastic, and hence because it is considered perfectly elastic, so there is no loss of kinetic energy during the collision. We assume that the time spent during collision is negligible as compared to time between successive collisions. For ideal gas, the total energy is in the form of kinetic energy only and depend on its absolute temperature. So these are the important points which we have to consider. Next, we try to understand the pressure exerted by a gas. So for this, we take a gas in a cubical box of face area A. We assume that mass of each gas molecule is m. Let us assume that the number of molecules per unit volume is n. Molar mass of the gas is capital M and volume of the gas is V. So let us consider a molecule moving with velocity V. So we can resolve the velocity vector of this molecule in 3 dimensions as Vxi plus Vyj plus Vzk. Now when this molecule will hit the wall normal to the x-axis with speed Vx, it will be reflected back with the same speed as the collision is elastic, as we have already discussed. As it will hit the wall, it will be returning with the same velocity. Negative sign here shows the opposite direction. So the change in momentum along x-axis will be final momentum minus initial momentum. So final momentum is minus mvx as shown in the diagram. So minus mvx, it becomes minus 2 mvx. Now number of molecules present in distance vx. Number of molecules present in distance vx will be NaVx. Why? Because small n is the number of molecules per unit volume. So n multiplied by volume covered AVx will give us the total number of molecules present in this volume. So only half of these molecules will hit the wall in 1 second and remaining will be moving away from the wall. So the momentum transfer to the wall per second will be half NaVx 2 mvx. We get this. So what will be the force exerted on the wall? Because we know that force is directly proportional to rate of change of momentum. So this will be mnavx square. So pressure exerted along x-axis, it will be Fx upon A. We get this mnvx square. So this is how we can calculate the pressure exerted by a gas. Similarly, along y-axis and along z-axis. So this is the concept of pressure. So taking average for all the molecules, we will get the pressure along x-axis as mnvx average square.